Hello everyone. I will present in English. Basically, the topic of this presentation is related to the interaction between the soil and pipelines when subjected to lateral loading. So it's an application related to the offshore industry. I am presenting on behalf of the authors of the paper referred here that was published in the Journal of the French Geotechnical Society in 2021. So here you will have some additional details about this publication. So this presentation is divided into 6 parts, following at some point the structure of the referred article, starting with an introduction in which I present a general overview of the problem studied, then the experimental setup employed in this research, and some details of the instrumentation utilized. In this sequence, we will see some details of the centrifugal model preparation and some of the results of the experiments. And as a closure, it was developed a methodology to evaluate the lateral forces due to clay pipe interaction and some conclusions of this research project. So long subsea pipelines tend to move over time due to temperature variations in connection with interruptions in production. So those displacements can take place in vertical and horizontal axis of the pipeline. And this research was mainly related to these lateral displacements that may occur in subsea pipelines. And this lateral displacement can be defined as lateral buckling, and it takes place or occurs when the soil pipeline friction is exceeded. Basically, in this example of a pipeline, it was designed to support at some extent controlled lateral displacements, and basically to accommodate this displacement induced by temperature and pressure variations. However, this approach requires a careful design to ensure that this buckling is developed as expected, and the fatigue response within this buckle is within acceptable limits throughout the operating life of the pipeline. In some more detail, we can see here the soil deformation pattern as a pipeline is subjected to lateral displacements. It can be identified some stages. At the first instance is reached a peak resistance. I don't know if there is a pointer here. Okay. So at the first instance is reached a peak resistance called also breakout resistance. At this stage, there is not a clear failure surface. Then, when after reaching this resistance, there is some kind of degradation of post-peak loss of tension, and we can see a two-sided mechanism developed in front of the pipeline. And as the lateral displacements are increased, so it occurs a large displacement with the formation of a berm in front of the pipeline. So in this case, we can see the development also of a failure surface. Well, also in this figure, for the context of this research, we can see the role of pipelines as arteries of offshore hydrocarbon developments. Different terminology is often used in the industry to distinguish flow lines that connect wells within a particular offshore field, and export pipelines that transport hydrocarbon products to the shore. In addition, the pipelines are classified according to the type of material. Rigid piles are made from steel tubes with diameters ranging from 0.1 meters to 1.5 meters. And there are also flexible pipelines composed of metal and polymer ranging in diameters from 0.1 meters to 0.5 meters. So with that being said, the objective of this research was to study the lateral clay pipe interaction. The centrifuge experiments performed consider large deformations. This implies the formation of the berms shown previously. And the parameters which were varied were basically the undulating shearing strength of the seabed and the different burial depths, which is the relationship between the burial of the pipeline with the diameter of the pipeline. So a set of centrifuge experiments were developed in the mini geotechnical centrifuge of the Federal University of Rio de Janeiro. This centrifuge was fabricated by the English company Broadbent, and regarding its characteristics, it has a diameter of 1.2 meters and can reach a maximum G level of 300 G. We can see in this illustration an example of a model in flight, and basically how is the behavior of the model container when it is subjected to the acceleration level of the centrifuge. So the model container employed as the space in which the centrifuge experiments take place has as dimensions 0.1 meters of wide, 0.3 meters of long, and a maximum height that can be achieved of 0.18 meters. And this model container is designed to support actuators that apply different types of loading, and additional supports to place, for instance, cameras for particle image velocimetry analysis or deformation analysis. So this kind of system is quite versatile for different applications. Regarding this, geotechnical centrifuge has been extensively used for oil and gas applications, but currently also there are new applications associated with renewable energies, with recent projects associated to monopiles under cyclic loading. In more detail, here we can observe the experimental setup, in which consisted of two types of pipelines with diameters of 9 millimeters and 15 millimeters in model scale, aiming at simulating pipelines of diameters of 0.3 meters and 0.5 meters at a prototype scale when subjected to a G level of 33 G. Regarding the instrumentation, one load cell was attached on top of a tube that connects the pipeline with the actuators on the top. So we have a vertical load cell and also a set of strain gauges, which at a first instance they measure bending moments, but then they are converted into lateral forces. In addition, this G level of 33 G was selected aiming at covering diameters representative of the industry, and also because to ensure the capacity of the actuators. So it's some kind of a balance between the capacity of the instrumentation and also to represent real conditions. Well, the purpose of this research was also to build two soil profiles, basically a weak or soft soil profile and stronger profile of clay, reconstituted clay, with undulating strength values that we will see in the sequence, around 4 kPa for the soft clay profile, and not that soft, of 14 kPa. The preparation of the model basically consisted in placing clay at a relatively elevated water content of 80% to ensure its workability. So then once the clay is placed in the container, some plates are placed on top of the model, and with different weights, aiming at applying consolidation pressures of 19 kPa for the soft clay and 120 kPa for the soft to stiff clay profile. The centrifuge was accelerated at 100 G, and then the consolidation is monitored by displacement transducers on top of the clay and pore pressure transducers to observe all the consolidation behavior of the clay. And the material used was spec white kaolin, which has extensive data sets, and they are easy to compare with other researches. So we'll move. Here we can observe some examples of the achieved undulating shear strength profiles measured by TWAR, which is also and the test takes place in flight. So we can see the differences between the two profiles of the soft clay and the soft to stiff clay profile. The experimental program consisted on 31 centrifuge tests by varying the burial depth between 25, 50, and 75%. So basically, this depth was increased, and the procedure was to move forward and backwards the distance, the pipeline, to a distance equivalent to 3 times the diameter, and 2 cycles of forward and backwards directions were applied. And basically, the velocity of these applications were selected to ensure that this load was under undulating conditions. Here we have an example of a typical lateral force displacement response for a pipeline with a burial depth of 25%. Regarding the lateral force, initially from O to R, it is achieved the breakout resistance, and with mobilized within a length of 0.1 times the diameter. Following the breakout, there is a slight increase in the lateral resistance, which is associated to the formation of the soil burn, and then in the backwards position, there is some kind of residual resistance due to the formation of burns in the opposite direction. And as the cycles take place, this resistance is at some point degraded. Basically, this research covers only the first cycle. Well, the results were compared with other experimental programs. Some normalization was necessary, basically, to have a comparative parameter. So it's observed a relatively good agreement between the experimental campaign and the results published by other authors. In addition, these results were also compared with an experimental with an equation proposed by also Oliveira et al., which is one of the authors. Also, there is a good agreement. Basically, we can see the parameters which can be easily interpreted: the result resistance, the diameter, the length, and basically the difference is this parameter N0, which depends on the type of soil. The author in 2010 worked with Guanabara Bay clay. So, for space white kaolin, it was calibrated for a value of 0.5. In the sequence, it was proposed an equation which considers the formation of the berm. And so here it is considered what happens after the breakout point. So it is added this parameter, which considers basically a parameter which is associated with a rate of increase of the height of the berm, assuming semicircular berms. So comparisons were made between the experimental results and the equation proposed. For the soft profile, it was observed a relatively good agreement between the experimental and the values obtained by the equation. On the other hand, for the profile, which is not that soft of clay, some dispersion was observed. However, the trend of the results is maintained. Here we can see in more detail the results from the equation and the experimental data for the soft clay profile, and some kind of dispersion for the second profile of the soft to stiff clay. And finally, we observed how the experimental data falls within a failure envelope, which is defined as a region that separates elastic and elastoplastic behavior of the soil. Here we see a comparison between the results and an experimental and a theoretical failure envelope. Here we have the reference. So basically, what we see is that the lateral soil pipe interaction reaches at a high rate the failure envelope, followed by an expansion, basically explained by the formation of the berms in front of the pipeline. And regarding the conclusions, so basically the normalized lateral breakout forces were compared with predictions, so showing a good agreement. So basically, in the region of the breakout points, the test also proved to be in accordance with file envelope curves, as the previous one shown. And basically, it shows that the forces reach quickly the yield surface, where a hardening phase begins, associated with the formation of the berm in front of the pipe. A simplified procedure was presented to estimate the normalized lateral force, taking into account the breakout resistance and the increase of the resistance due to the formation of the berm. And finally, some comparisons were performed between the experimental data and the equation proposed, and good correlation was achieved. However, further investigation is to be carried out to validate this approach. And that's all for the funding institutions.